yourself into. What you're going to be doing in Lab 1, you're going to be designing your own ISA. What is an ISA? An ISA is an instruction set architecture. So the ISA is an agreed-upon interface between all the software that runs on a machine system and the hardware that executes it. It is part of the computer architecture that is visible to the programmer. So what it is this right here. You have your application compiler operating system, and then beneath that you have your instruction set processor, your CPU, IOs, digital design, circuit design. But what ties those two things together? That's your ISA. That's like the middleman that's going to be communicating between those top block and bottom block. So what's in an ISA? An ISA has, or what's in an instruction that composes your ISA? You have opcodes. Opcodes are just a breakdown of what instructions are available to your processor. Technically, opcodes are just the bits that are denoting what those instructions are. It's like an encoding. So if I have 16 instructions, how many bits I'm going to need for that? I'm going to need 4 bits for that. So that's what an opcode is. It's just an encoding that tells the processor what that instruction is. What else is in an ISA? We have registers, and there's different types of registers. There's general purpose or special purpose registers, you know? I don't know if you guys took CSE 30 here, you probably did it with Spark. And then in 141, you're going to be doing some assembly and MIPS, and there's some special registers that they have listed there. So an ISA is going to have that. Instruction formats. So instruction formats are, what MIPS does, it's a good example to always use because that's what you guys are going to be doing in 141, is they group together different kind of instructions. So there's 3 main types in 141 for MIPS that you're going to learn: R-type instructions, I-type instructions, or J-type. R-type means arithmetic instructions like an add or a subtract or an XOR or an OR or an AND. An I-type instruction is something that you're going to do with an immediate value, like you want to load the immediate value of 5 into your register, or you want to branch backwards some amount. So when you're doing MIPS, you guys are all used to like doing branch and then a label, like branch label 1, like beginning of the loop, or branch outer loop. So in this class, we're not going to be doing labels because we're not doing a compiler. In the later labs in Lab 3, we're going to do an assembler which converts your assembly code that you guys are going to be writing for Lab 1 into machine code. So you're not going to be able to write a label in your assembly code. You're going to have to specify in some way of how to branch forward or backwards. What else do we have in an ISA? We have storage access and addressing modes. Storage access refers to data memory. So your ISAs you're going to be doing something with data. So that data is something that's coming from the outside. So if we look at the assignment, hopefully you guys have read this by now. We have some values, like we're in the first program, number 17 here, we're doing A times B. So how do you know what A is and how do you know what B is? Those values are living in data memory. So you're going to have to come up with a way to access those values and do operations on them. And then same with 18. Professor Eldon was talking about a 4-bit pattern. Where does that 4-bit pattern live? It lives in memory, and you're going to be reading that and then checking it against something and doing stuff with that. And then same with 19. You have an array. So let me go back to 18 real quick. In 18, you're checking an array of 64 bytes. So those 64 bytes, those are all in data memory. So at position 32 to 95, 64 bytes, those are all right there. They're going to be in data memory. You're going to have to do stuff with that and access them and check to see if there's a pattern there. Same with 19. You have an array of 20 bytes. That stuff lives in data memory. Let's go back here. Oh, yeah, sorry. Cool. So this is sort of like a roadmap of what you guys are going to be doing in this class. So it's not in the order that we're going to be doing things. This whole thing in lab 1, what you're doing is you're setting the roadmap for the rest of the quarter for lab 2, 3, and 4. Lab 1 is your ISA. That's going to tell you how you're going to be doing things and like how this whole picture will work together. So what you're doing in lab 1, you're going to be designing your ISA and then also coding those 3 programs, 17, 18, 19, in your own assembly language. So that assembly language would be your assembly language program. In lab 3, you're going to be doing an assembler, which is going to take that assembly code that you guys made up and convert it to machine code. And then in lab 2, 3, and 4, you're going to be coding your processor, and it's going to run that machine code and run those programs. Go on. So famous ISAs, you guys probably heard of these. Intel x86, very really famous, still used today. MIPS, ARM, Spark, these are 3 that you've probably used. PowerPC, it's another IBM one. It's found in PlayStation 3s. Intel IA64, you'll learn more about that stuff in 141. So I'm going to go through, real briefly, different types of ISAs. You're going to be learning more about this stuff from Professor Eldon in next lectures and in 141. You're going to be covering that hopefully within the next week in that class and week after that. So I'm going to show here 4 different types of ISA classes. So there's an accumulator, a stack, a general purpose register, and a load store. What you guys are probably more familiar with if you've done MIPS or Spark is load store. So I'll start up from the bottom and I'll go up. So load store means that any operation you're doing, arithmetic, you're always bringing stuff into the register and doing some operation on them and then storing it back into a register. You're never operating on data in memory. You're always loading things in, doing something, and storing them back out, hence load store. And a general purpose, which is what x86 and computers today are, is you're allowed to do operations between registers and memory. So what that means is your ALU, your arithmetic logic unit, it has inputs coming in from memory. So you can do an operation between a register and something in memory. And then there's the stack. So a stack is like, you guys are all familiar with the stack. So I don't know if you guys have done like prefix or postfix, like mathematical operation sort of programs where you have a stack and you do things that way. So in the next slide, I'm going to show examples of each one. And then accumulator, think of an accumulator as like a simple basic handheld calculator. You enter a number and it stores it, and then you hit +5, and then what's in your calculator is that like added number. That's what an accumulator is. So this is some examples. So let's say we want to do this operation of A equals BC plus XY. So A, B, C, X, Y, they're all in data memory. So in a stack, what you would do is you would want to push B from data memory onto your stack, push C from data memory onto your stack, push a multiply instruction onto your stack, and then when you pop those, you're going to get the product of B and C. So that's what's going on, and you guys can go through that. So once you get that, at the top of your stack is going to be BC. And then you're going to have XY, and you're going to do mult on that. You're going to get BC and XY, and then you're going to have add. So then you're going to add BC and XY, and then you're going to store that into A. So with the accumulator, it's like a calculator example, like I said. You're going to load B, like on a handheld calculator, you're going to type in whatever value of B is. You're going to hit the multiply, and then you're going to hit like whatever the value of C is, and then you're going to store that back into memory. And then you're going to load X, multiply times Y, store that back into memory, and then, you're going to add that to temp, which is in memory, and then store that into A. So you can see here, in stack and accumulator, you're sort of accessing data memory more than you normally would compared to these other ones. So in RegMem, it's just operating on stuff from memory, like directly. So that one is always sort of operating on stuff in memory. And in reg, which is your load store, the first 4 things that we do is we're loading in those values from data memory. B, C, X, Y, and we're putting them into their own registers, and then doing multiplication on them, and then adding them, and then you can see all these are different registers, and then you're storing it back out. So that's, I hope you guys can understand the difference between these couple of, like, 4 different ISAs. If you have any questions, just feel free to interrupt me or raise your hand. But what we're going to be doing in this course is we want to do a program-specific processor. What that means is that you don't want to do something too general like MIPS. MIPS works with any program. MIPS is in a lot of embedded processors. You can write tons of code, whatever you want to do, and it'll run that. But for us, we just care about running 3 programs and nothing else. So you want your ISA to be application-specific, meaning that its functionality is only to run the 3 programs and not anything else. So we're trying to be lean here. You don't want an overly general-purpose ISA processor that can run any program because, 1, this would be really inefficient for the 3 programs that you're doing. You don't want to do something that's too slow or have a lot of instructions just to implement your 3 programs. Second one, I feel like this one is really important too, is that you only have 9 bits for your instruction. You can't, I mean, it'd be a really, really hard task to make a general purpose processor just using 9-bit instructions. You can only do so much, but you can do enough to do these 3 specific programs. Third one is that when you do a program-specific ISA processor, what that lets you do is you can come up with your own special instructions. By doing that, that'll make your assembly code more simple. You don't have to do a bunch of steps. Maybe you can find a way that you're going to come up with an instruction that does 2 things or 3 things or something like that. That will make your assembly code a lot cleaner. And I'll give some examples of what I mean by a complex or a special instruction, stuff that you're going to be coming up with. What you should aim for in this class is to come up with a hybrid ISA architecture. So what you want to do is you want to borrow bits and pieces of all of these or some of them, some combination of them, so that you can come up with the optimized version of an ISA or processor, something that makes coding your 3 programs in your own assembly language simpler and also utilizing those 9 bits for instruction to the fullest. You don't want any bits just hanging or not doing anything. Everything in those 9 bits should be doing something. All right. Did that. So this is that picture Professor Eldon went over in class. So this is what we're doing. So when you do your custom or special instructions, what you're essentially doing is you're making a custom ALU. So let's say I had an instruction that, or I had a purpose or something I need to do where I add 5 and subtract 3. I can make that into 1 instruction compared to 2 instructions where I would add and subtract. You can make a custom instruction that does that. That's totally legal. So that's a brief example of what I mean by a custom or special instruction, and that means that you're going to customize your ALU in the future labs. So this is more pertinent to what you're going to be doing in Lab 1. So in Lab 1, you have to decide how many instructions are you going to have. So I made a Piazza post on this. Hopefully you guys should definitely read this. What it basically says is that this is what I did last quarter and what helped me out a lot, was that you want to write pseudocode or C code or C++ code for those 3 programs and then sort of break it down from there. Once you write out pseudocode, you can see what operations you're doing using a higher level language, like, hey, I'm adding or I'm shifting, I'm doing something, I'm XORing, I'm ANDing, I have a bit mask, whatever. So once you do that for all 3 programs, you have a better idea of what instructions you need and the total number of them. So hypothetically, let's say you come down to a number like, hey, I'm doing 12 different operations or instructions. So ceiling log2 of 12 means that I'm going to need at least 4 bits for an opcode to represent each of those instructions. So right off the bat, you have 4 bits used up of your 9 bits. You have 5 bits left. And then what you decide to do with those 5 bits comes into operands. So operands refers to registers. So in like MIPS or Spark code, this sort of looks familiar to you guys, add R1, R2, R5. So in MIPS, it's a little different from Spark. What this means is R1 is equal to R2 plus R5, the values in them. So over here, this is RTL. It's called Register Transfer Logic or Language. It's just a quick way to show what instruction is doing, just in like higher level language. That's what that means. So operands. You're allowed up to 16 registers max, but do you want to use a maximum of 16 registers? Let's say we do have 16 registers, so that means we need 4 bits. We already used up 4 bits if we had 12 instructions, and then I have 4 bits to address one register. So let's say I'm doing add R1, R2, R5. Add would be 4 bits, because I need to specify what that instruction is in the opcode. And then each one of these would be 4 bits. So that's 16 bits. That's 7 over the 9, so I can't do that. You guys have to get creative and figure out ways to do some tricks or hacks to represent more data just using 9 bits. You have to do some encoding, and I'll give more examples of that by what I mean. Location, that's just specifying like your order. That's totally up to you guys of how you want to write out your assembly code. I mean, just be consistent with what you do throughout everything. So like over here in MIPS, R1 is equal to R2 plus R5. So that's just one way of doing it. It could have been that your destination register could have been R5, so it could have been R5 is equal to R1 plus R2. It's totally up to you. Types. So over here, if we go back to this guy, accumulator. So if I had different types of registers, so let's say I'm using 8 registers, and I say one of them is an accumulator register. So I have 7 general purpose registers and 1 accumulator register. What that means is that I can use this special register, R accumulator, and use that in an accumulator fashion, where if I'm doing an add instruction or a subtraction instruction, it'll always do it on the accumulator register. That's what I mean by type over here. Sorry. How to specify, that just means how are you going to encode it with your opcode. You want to make a list of like what bits represent what. So let's just say I have 8 registers. What that means is that 0, 0, 0, I need 3 bits. So 0, 0, 0 would mean register 0, or the R accumulator register 0, 0, 1 would be R1, 0, 1, 0 would be R2, and so on. That's what that means. Instruction format. So this one is a little important. Instruction format. So I'm going to give a MIPS example. You guys are going to be looking at this sheet a lot in 141, the MIPS screen sheet. This is just like a table that shows you all the instructions that MIPS has available to you and what. So if you look at all this stuff over here, opcode / func. So they're giving you the opcode in hex, and they're giving you something called func for function, and I'll talk about that in a little bit. But this green sheet, what it does is it lists all the instructions that are available in the MIPS ISA, and it gives you the RTL of what each instruction is doing. So it's that same thing that we saw just previously. And then instruction formats. So this is what I was talking about, R-type, I-type, J-type. R-type was for arithmetic instructions. I-type was for immediate value instructions. J-type was for jump instructions, but you guys don't need to worry about this in too much detail. But what this means is you have 9 bits. Over here for MIPS, they have 32 bits. So let's say you get your list of 12 instructions or whatever, and then you specify that, oh, hey, like 6 of these are arithmetic instructions, 4 of these are immediate value instructions, and then 2 or something else for like your branch or something, whatever it is. So you want to specify what those are when you're designing your ISA, and that's going to be required in the report. Let's go on. All right, so when you have 9 bits instructions, how are you going to decide how you want to allocate your 9 bits? So these are just some questions and pointers that will help you decide what to do with those 9 bits. How many bits will you need for your opcode, which tells the processor what instruction it is during the decode stage? Are you doing something like MIPS, using a function code for R-type instruction? So if we go back over here, MIPS does their own trick or hack. What they do is they have, if you look at all these arithmetic instructions, add immediate, or not add immediate, yeah, sorry. Oh yeah, sorry. So if you look at add, they give an opcode of 0 and a function code of 20 hex. And then let's look at AND. They give an opcode of 0 and a different function code. So how can 2 instructions have the same opcode but and mean different things? What it does is that if the opcode is the same, it goes and looks at the function code, which is over here. So if the opcodes are zeros here, it's going to go look at the last part of the instruction, and it's going to be something different. So what they're doing is they're almost like multiplexing off of one opcode to get 8 instructions. You guys understand what I mean by that? So you can do the same trick like what they did. So let's say you have 8 instructions. That means you have 3 bits for opcode. And then you're doing something where you only need to specify 1 register operand. So like whatever instruction it is, what's an example with you only need 1 register operand? Let's say you need to negate a value. Like if you need to get the 2's complement of something, you just need to specify 1 register operand because you're only acting on 1 data entity and you're storing it back in the same register. So you can do that where if you have 3 bits for opcode, specify a register 3 bits, and then have a func code for 3 bits. So what that lets you do is from 1 opcode of 0, 0, 0, whatever it is, it lets you get 8 instructions out of that just from having that function code because you have 3 bits at the end. But the downside is that you can only do a 1 register operand operation. Are you guys following me? So if you have, let's say we have 8 or 3 bits for opcode. Technically, that allows us to only have 8 instructions. But by using a func code, we're able to get more instructions because the 3 bits specifies 8 instructions. The next 3 bits would specify a register. If I had 8 registers, like 3 bits, 3, 3, 3. So we have 8 max registers. And then the last 3 bits would act as a function code. So a function code lets you get 8 options per opcode. So you can have 0, 0, 0. Let's just say that the opcode is 0, 0, 0. You can have function code from 0, 0, 0 to 1, 1, 1. So that gives you 8 options. But the downside is that you can only do an instruction that uses 1 register. So like you can't add 2 numbers unless you're doing an accumulator where you can do some trick where I just specify 1 register. That register, I'm always adding it to the accumulator register. That's what I mean by that. You had a question? Okay. Was it regarding like an accumulator, like what do you do with 1 register? Yeah, okay. So that's what I mean by that. Moving on. How many registers will you need? So if you have 8 registers, 3 bits, 16 registers, 4 bits. Also, how many register operands will instructions have? So if you have 8 registers and 3 register operands, then that's 9 bits already. So you have no bits left over for your opcode. That's not good. You have to specify an opcode. How will you handle immediate values in your instruction? So when you're accessing data memory, you have to specify an immediate value. Or when you want to load in some constant, you're going to have to specify an immediate value. How do you handle that? So you're going to have some instruction to load in an immediate value or not. There's different ways to do this. So let's say I had 3 bits for opcode, and one of those 3 bits, or one of those 8 options for an opcode was for loading an immediate. That leaves me 6 bits for an immediate value. So as an unsigned number, that's 0 to 63, and then that you have a limit of loading in values of 0 to 63. But that's just one option. You guys are going to be coming up with your own solutions for this. How will you handle branching? So relative versus absolute versus XYZ. What do you mean by relative is when your program is running, you're going to have something called a program counter, your PC. So what relative branching means is that, hey, I need to move forward 5 instructions relative to my PC or 5 instructions backward relative to my PC. That's what relative means. Absolute branching means that you're going to specify what PC value you want to essentially jump to. And then XYZ method is something that you could come up with, is that, hey, you don't want to do relative and you don't want to do absolute. If you can think of another method that works, you're more than welcome to. Let's see. Other things for key ISA decisions. For regular arithmetic instructions and operations, especially, this is really important for the multiplication one, how are you going to handle overflow? Should you even care about overflow? So overflow, are you guys familiar with overflow? So if you have like an operation where you're adding something and there's overflow, or if you're doing a shift and you need to care about the bit that you're shifting out, you have to have some way of taking care of that overflow. How we handle negative values, more specifically, do your instructions need to be unsigned or signed? So if we look at MIPS, they have 2 different add instructions. This one refers to just like it could be regular addition between negative values and negative values, just adding 2's complement values. And then they have add unsigned. This is addition just for unsigned numbers. So you have to decide, do you even care about sign in some of the problems? So in 17, you should care about, in the multiplication one, you should care about sign. And the other ones, in 18, sorry. In 18, you're not really caring about sign at all. You're just doing pattern matching. So you don't need to worry about anything there. And then in farthest pair, do you care if these values in the array are negative or not? No, not really, because you're just looking at the bit the bit values. You don't care if the number, or if this thing is signed or unsigned. That's what I mean by that. How are you going to handle conditional operations? So when you write your pseudocode for these 3 programs, you're going to have if, else's, whiles, whatever in there. So how are you going to implement that in your assembly code that you come up with? You're going to have some form of a conditional, like a set less. So if we look at conditionals in MIPS, they have instructions called set less than, and then you can come up with their own set greater than, or is it equal, something like that. You can come up with their own instructions. They have branch on equal. I mean, that's one. So conditionals come up in when you're doing loops. So when you're doing shift adds for multiplication, you're looping technically 8 times because our data path is 8 bits wide. So when you do a shift and add and you need to go back and look at the next value, like to do the next iteration of that loop, how are you going to be able to branch back? You're going to have to check some condition that, hey, have I done 8 iterations or not? So you're going to have some logic or control flow logic in there to handle that. So this is all up to you guys on how you want to do these things. There is no correct solution. Last quarter, a bunch of people did a lot of different stuff. No one really, there was some overlap. People were doing sort of the same thing. But for the most part, people were really creative, and they sort of came up with solutions that they thought worked. So that's what we encourage, is to be creative. Reminder of restrictions. So there are some ground rules of what you can do and cannot do, but there's very few things that you can't do. Everything else is pretty permissible. You can have a maximum of 16 addressable registers, and that doesn't include a 1-bit overflow register. So if you have a 1-bit register to hold a value for overflow, that's totally legal and doesn't count against 16. And if you decide to go with the stack architecture, that stack pointer register won't count against that 16 either. Another limitation is you can only write to one register per clock cycle, but you can read out from a register file as many registers as you want. So you can read however many registers you have at once, but you can only write to one at a time. Data memory, you can either read from data memory or write to data memory in one clock cycle. You can't do both because those are clocked operations that requires a clock to either tell you to read or write. You can't unroll your, yep, question? You can only read and write 1 byte because the data path is 8 bits, 1 byte. So that bus line that you have going to data memory, that's only 8 bits wide. So you can only read and write 1 byte. You can't unroll your loops. What does that mean? So you can't just copy paste your assembly code 8 times if you're looping for 8 times. You can't do that. That's just going to make it really ugly. Your instruction memory is going to be massive. What else? Your ISA processor has to be a single cycle implementation. What that means is that your instruction occurs in one clock cycle. High, low, that's the end of one instruction. You're going to be learning more about this in 141. For those of you who have already took it, you already know about single cycle. Move on. Quick definitions. So we're going to ask you to give us dynamic instruction count. What does that mean? So static instruction count is how many instructions or lines of assembly code you have for a program. We're not asking for that in the questions that we have over here when they ask for it's somewhere in there, one of the questions right here. In what ways did you optimize for dynamic instruction count? What that means is dynamic instruction count means how many total instructions or lines of assembly were run to finish your program. So let's say you have 60 lines of assembly code or 60 instructions to do the first program. That doesn't mean that 60 things occurred in the processor to finish the program because you had loops, you know? So you're going to have to just do it by hand, and you're going to have to calculate like what is your dynamic instruction count to run a program. Use tricks and hacks to help optimize. So you want to be creative. So this is what Professor was saying, is you want to think of outside-the-box solutions. And this is what I'm allowed to say. And if you come and ask me questions on what you can do, I'm more than happy to help. So this is just one example. Lookup tables. Can you represent larger values using some encoding? So what that means is, let's say you have some bits left over for an instruction, and you need to access a lot of like that. So let's say in your program, you're branching, and your branch distance, like your branch forward and backward, is you're not doing it many times. So for the multiplication one, you're either branching back some fixed amount or branching forward some fixed amount. So do you need to put that immediate value of that fixed amount, or can you encode that in a way that, hey, I only branch 4 times in a program. Maybe I can do some sort of encoding so I don't have to load up an immediate value that's that big. You can hard code these things, is what we're going to be doing in Lab 2 and 3 and 4. What else? Complex instructions that pack a lot of functionality, as long as the rules and constraints aren't broken. So those rules and constraints that I had on the previous page, you don't want to break those. So a complex instruction, if we look at some of these programs, string match. That's a good one where you can possibly have a complex instruction. What I mean by complex is, do you need to, if you have a 4-bit string and your byte is 8 bits, how many places are you going to be checking to see if that pattern exists in a byte? Does anyone know? How many 4-bit positions are there in something that's 8 bits? Anyone? 5. Yep, so do you need to check all 5 of those in 5 different instructions, or can you possibly do that in one instruction? Because that's just hardware. That's just XOR gates and however you decide to do that. Do you have to look at it and then shift and then compare and then shift and compare, or can you have one magical instruction that looks at all 5 positions at once? Totally can. That's what I mean by complex instructions. Does that make sense? Does anyone have questions on complex instruction? What else? Let's move on. Things to keep in mind and miscellaneous suggestions. The data path of your ISA processor is 8 bits wide. That means that your registers and data memory, you can't be, what that gentleman asked before, you can't be reading and writing multiple bytes. You can only do 1 byte at a time. And these are some recommendations that I have. When you have outlined your ISA design, make something that's like a simpler version of this, just a green sheet, like my opcodes are this is what that opcode refers to, or func code refers to, and then have like RTL in there that said like what that instruction does. So that's going to be helpful when you're coding your assembly for these 3 programs, because you can reference back to that real easily. You don't have to go back on what you had in your head, And then this is going to be really useful in the future labs, just having a simple green sheet. You can do an Excel or Google Sheets or whatever, and you're going to be using that when you're doing your Verilog code or system Verilog code for the other labs, just as a reference to go back to, like, hey, this is what this instruction is, like, bitwise, This is what the opcodes were. This is how many register operands I had, etc. And then really important is double and triple check your assembly code that you write for these 3 programs. So you're going to be coming up with your own assembly code, and you're going to be coding the 3 programs. Double and triple check that. If you do this, your life is going to be way easier in the future labs. Definitely lab 1 is the hardest lab, and then labs 2, 3, and 4 are pretty simple in my opinion, because a lot of the work, it's very front-loaded. So if you do a good job in lab 1, 2, 3, and 4 are going to be relatively easy, because your assembly code, you have checked it and the logic was correct, so you know it works. And what I mean by check it is do it by hand on a piece of paper or whiteboard, like step through it, like do each instruction, do like a couple of iterations of a loop. Is it making sense? Do it on your own examples. And if it works, then most likely in 2, 3, and 4, when you code it all out, it's going to work. That's what I mean by that. Let's go over some of, So I'm just going to explain some things in here that could be a little vague. Write a program that finds a quadruple precision sign product of 2 signed double precision numbers. When he says double precision numbers, we're not talking about decimals. Double precision means that we have a 16-bit value, a 16-bit signed number, but our data memory is only 8 bits. So what that means is that location 1 is storing the high bits, and location 2 is storing the high 8 bits, and then location 2 is storing the low 8 bits. So it's just splitting it up into 2 locations in memory. That's what he means by double precision. And then if you do multiplication of 16-bit value times a 16-bit value, what is your product going to be? Does anyone know like how many bits wide? Yep, 32. So your result is going to be 32 bits wide, and I think he only cares about the 16 lower bits in this. Oh, no, sorry. We changed it. So you're going to have to write all 32 bits of whatever that product is. So keep in mind, like, just look up, are you guys familiar with binary multiplication? In 140L, they sort of do it briefly, where they talk about some algorithms for it. But regular binary, like unsigned binary multiplication, it's pretty simple. It's just like doing multiplication as you did as a child, where you just write down numbers and you put an X and you shift things along, Binary multiplication is the same thing. Signed binary multiplication is almost the same thing, but you just got to worry about sign. And then do sign extension if it's negative, set your sign bit, etc. String match is pretty straightforward. This will probably be the more easier one to code for you guys in your assembly language. And then farthest pair. This one, you're looking at the Hamming distance. Hamming distance means is the number of differences of zeros and ones. So think of what bitwise operation you could probably do and what other things you can do to figure out what the difference was. That's pretty simple. Another thing to keep in mind is, let's say you have all zeros and all ones, and this is your array. So let's say the first two values, or the first value was 0, and the second value was all ones. So it would be minus 128. It would be minus 128. So let's say the first two values in your array were those two, and that would give you a Hamming distance of 8. And we're asking for the greatest Hamming distance. So let's say along the way you figure out that your Hamming distance is 8. That means you can just break out of that loop and write that value, because you're not going to get a Hamming distance greater than 8. So you can have that in your assembly code where you can check that. That'll help further optimize your program's execution and save on execution time later on. We're not grading on execution time or anything like that. The most important thing is that your programs are working correctly. So you don't need to worry about execution time or crazy optimizations. Just make sure it works. That's the most important thing. What else? Any questions? Yeah.
How big are registers?
Like wide?
Yeah.
8 bits. 8 bits, yeah. And you can have up to 16 registers, but you may not want to have 16 registers. It's totally up to you. The design is all on you guys. So be creative, Think of cool ways to tackle these problems. Anyone else? Yeah? Yeah, these are already on Piazza. I put it in under resources. Yep. So, yeah. Which one? Oh, of the lab? Yeah, I'll put that up. Yeah. I just really want to reiterate to you guys, it's a 2-unit course. If you clump up the work and sort of procrastinate, it's going to feel like a lot more. Just do your due diligence right now, and it'll feel like 2 units later on, Trust me on it. Just do a lot of work now, and it's going to be really smooth later on. Yep. That's it. That's all I have, guys.
We have special registers outside of those 6